Hello, I'm Ashley Ford for SIPT. I'm an associate professor in the School of Chemical Engineering at Oklahoma State University, and my presentation is titled Choose Your Own Kinetics Adventure, Student-Designed Case Studies for Chemical Reaction Engineering Course Projects. Some of you may remember the Choose Your Own Adventure stories. This was a series of books and a number of spin-off books from other companies, which were essentially stories that involve fictional storybooks that involved choices that you as the reader would make that redirected you to various page numbers if you chose option A, or a different page number if you chose option B, and your path through the story would be different than other readers if you selected different choices along the way. And so there were a whole host of these. And so they follow this branching pattern towards multiple possible endings. Based on the fork that you choose, there may be some interconnection and overlap with other people who might be reading the same story, but it does not follow the classic linear progression. And so you have this initial situation, an option, there's some consequence of choosing an option, and you keep flowing through this series of choices and options with consequences. This Choose Your Own Adventure structure was adopted for chemical reaction engineering course projects. So the idea is that I give the students a project statement that has some initial situation, and for this class, the initial situation is that they are working for a company and they're charged with identifying a new to the company product. It could already exist, but something that they can manufacture using a chemical process that they are doing the initial reaction engineering design for. And so they get to choose a topic of their interest, and each student or each team of students may have different topical areas of interest, and I actually encourage them to form teams based on their interests rather than based on their friend network. Sometimes they form with friends, but many of them will choose if they know they're interested in the petrochemical industry, or they're interested in biotherapeutics or other types of materials, or they may just be interested in learning more about beer and fermentation processes. So they choose an option, and then there's consequences. After they choose that option, then their pathway looks different than other students who may have chosen a different topic. Each of the projects is required to consider multiple reactions and a catalyst. So depending on what data they find and which reactions and catalysts they choose, then they're going to have different processes that they need to consider, and they all have to choose a heat transfer mode. Now that's going to look different for fermentation processes than it would look like for the Haber-Bosch process, for example. And so every team in the class potentially has a very different flow through this diagram. So the goal of this project, overall goal, is to engage students through problem-based learning. And so they're getting experience with real-world problems beyond the scope of those typically covered in undergraduate textbooks. And so there's major concepts in the course of catalysis, multiple reactions, and heat transfer, but those are not blended together in very many problems in the entire text. And so this project gives them the opportunity to weave those together and to solve realistic problems that involve all of these aspects. And we're trying to give students opportunities to explore industrial applications in areas of interest to them in particular. So they may choose traditional chemicals, fuels and petrochemicals, food and beverages, pharmaceuticals, biotechnology. Some students have thought to do something with explosives or other types of chemical compounds, but then they quickly found there's some, many of those manufacturing processes are held private, and so they need security clearance in order to use those, so they're not appropriate for a course project. So the assignment is typically about 6 weeks long. Teams of 3 to 4 are preferred, and their main tasks are to identify a topical area to design a new chemical product for this company and make the choices appropriate for the option that they've selected. They are tasked with searching the literature for data, and I provide instructions to them about how to use our libraries databases for reading and accessing chemical engineering or chemistry related publications and finding kinetics data. They determine the best reactor conditions for the system using Fogler's textbook, The Chemical Reaction Engineering Algorithm, and the design principles covered in the course. So once they've set up the problem and found the data, it's essentially the scope of a homework problem, but they don't realize that they're creating their own homework problem. We have a checkpoint where they have a one-page preliminary report sketching their path through the options and identifying references, and we meet together to discuss that. So I meet with each of the teams to discuss the appropriateness and the scope of the project that they've proposed. And in their final submission, they have a project report, a polymath simulation of predictions of the system that they're studying, and the figures that are generated by polymath for the selected design. This project connects 10 out of the 11 of our course objectives. So they are identifying, understanding, characterize chemical reaction rate laws, size and modeling continuous and batch reactors. They probably are doing one or the other of these steps. They are looking at reactor principles for design. They're modeling multiple reactions. If they have a gas phase process, they're modeling pressure drops and changing stoichiometry. They are considering catalysis. They are interpreting data. They are also using computer packages, specifically polymath. They are completing a group project, explicitly one of the course learning objectives. They're working on their team skills with working with other students, and they're presenting written work. I've taught this course 6 years. This is a junior level kinetics course at Oklahoma State University. Each spring it's offered. And the most popular of the projects is fermentation. So in 1 year in particular, 8 out of the 17 teams chose fermentation. And this might look like beer most commonly, but also wine, sake, tequila, scotch, champagne, cheese. Lots of students choose to study the fermentation processes. We also, for the fermentation, go to a brewery and do a tour there, and so then I ask them to incorporate some of the elements of things that we talk about on the tour. The Haber process has also been very popular for ammonia synthesis. There's several publications with data of different catalysts for this ammonia synthesis process. Some students have looked at production of high fructose corn syrup from corn using enzymes, and so thinking again about starch and enzymatic reactions. Methanol from syngas is a perennial favorite. Several students have looked at that. There are quite a few catalysis papers that are published that involve different reaction mechanisms for this and the appropriate data the students can extract. Ibuprofen synthesis is popular by our students that are interested in pharmaceutical technologies. And transesterification to produce biodiesel is also a choice that students that are interested in more green technologies, biofuels, there are published papers in this topic that students can use. And in these different projects, they might have different design criteria that they select for themselves. So one team was interested in biodiesel on having a certain product purity. Others were looking at the raw material being rendered pig fat as a leftover waste material, and so the goal was to consume as much of the raw material and convert it to any higher value product, less concerned with the product purity as the overall objective, but the optimization objective was to consume as much, convert as much of the raw material as possible. And so how can you objectively grade designs for this choose your own adventure style of projects? And so with each group getting different topics, there's no feasible way for the instructor to have one right answer or a range of answers. But it also means that you as the instructor do not need to generate the sample solution in advance, which is very helpful if you are crunched for time. So I evaluate the report more from a project manager's perspective. The writing is scored from a fine-grained rubric with specific things they need to include. The complete path, so must be covered. So they have to have multiple reactions, they have to involve catalysis, and they have to involve heat transfer. And the methods from the chemical reaction engineering algorithm must be followed, but these are used in all of our homeworks and exams in the course. So they have to define their mole balances, the rate laws, stoichiometry, energy balances, combine those equations, and numerically evaluate this to solve that system of equations using the polymath software. So these are key things that they're doing throughout the course. And so this Choose Your Own Adventure project structure was used for the last 6 years in the Chemical Reaction Engineering course projects at Oklahoma State University. I love this system. I came in as an assistant professor not knowing what to do with a course project in a class, and thought, how about having the students generate their own topic ideas? The students have loved it. There's been such a diversity of topics. I get to meet with all of the students, and that's really helpful, particularly in the spring 2020 when we went online for the COVID crisis. This was a really important check-in time with the students that all of them knew in advance they would be meeting with me, and we could talk about other things as well, but it got them all into my virtual office hours, and before times it got them into my actual office. And it was, some students would normally come to office hours, but many would not. And so having this time where every student needed to come to my office and talk to me was really important for the culture of the class. Also, I could help students see what the scope, some of them might propose too little or too much, and we could rein that in. I also really like that trying to align the writing rubric with the same rubric that my colleagues use for the unit operations lab that the students are taking concurrently, and so that their same types of writing style, rules about headings and font sizes and all of that are also emphasized. Additionally, our students this spring had the opportunity to start to work with some of the digital tools. So I encourage them to use Google Hangouts or Zoom for having group meetings. I encourage them to be using other types of teamwork related software, things like Google Docs and Dropbox for sharing files, not any specific brand tools, but I could help them with that. And there was no differences in my expectations for how a project had happened from working remotely, because many of you have found that we're able to do many of our normal things through remote interactions, and so that was not an obstacle. Certainly I was flexible and had some grace in deadlines with the students, but I didn't change the actual procedures required for this group project because its nature was already very flexible and allowing students a lot of choices and options. And so I would continue to use this course or this type of project in this course or other similar core undergraduate courses. I think it provides a lot of freedom for the students to really customize their experience, and I've had several talk about how they've been able to use these design case studies in interviews that might be different than the kinds of projects that our senior design class might come up with, which tends to be all of the students following after the same design charge. Here the students get some say in what they choose to study. If you have any questions, please feel free to reach out to me by email or on Twitter. And additionally, in the iPosters, I have provided a Dropbox folder that includes my instructions and some other resources related to this project, and a manuscript that I wrote a couple of years ago related to this project. So please feel free to ask me any questions you have about this topic.